Hi guys, it's Mrs. Millicent. Okay, let's wrap up this section, wrap up this chapter. Why do we care about least squared regression lines? Okay, well, because we want to be able to gather data, okay, see if there's a correlation between the data, and then create a least squared regression line so we can make predictions. We can try to figure out what's going to happen, okay? Now, we want our predictions to be as accurate as possible, so that's what we're going to talk about today, okay? All right, so let's just do a quick little analysis of this situation. Your friend is visiting from Texas and asks, what does a hamburger cost in this town? This caused you to wonder because the price of a hamburger seems to be different at every eatery. So you think there might be an association between the amount of meat in the patty and the cost of the burger. So you use a website and you create a scatter plot with a least squared regression line, residual plot, and some summary statistics based on the amount of meat and price of hamburgers at 15 different restaurants in town. Okay, so we actually got our least squared regression line, okay? So we have our y hat, oh, my pen's all blobby. We got our y hat, and there's our x, okay, and there's our slope, or our y-intercept and our slope. And we have our r squared, which is our coefficient of determination, and we have our s, which is the standard deviation of residuals, okay? So let's do a couple things. Let's check the least squared regression line against the point of their means. All least squared regression lines have the coordinate of the means. Okay, so let's see. Meat was x, cost is y. So this is the mean of my x, this is the mean of my y, this is standard deviation of my x, this is standard deviation of my y. Okay, so if I go to 5.2, so maybe like right here, and then if I hit my least squared regression line, this should match to about 4.1. Yeah, pretty good. Okay, so this would be my mean, my coordinate made up of my means. Just wanted to say that, make that little statement. Okay. Now clearly I can see for my least squared regression line, some of my predictions, or some of my actuals are larger than my predictions, some of my actuals are less than my prediction. Okay, so I'll have positive residuals and negative residuals. Okay, let's interpret the slope and y-intercept while we're here. Okay, so this is saying for each additional ounce of meat in the hamburger, I predict the cost to increase by about 73 cents. Okay, so my slope is don't forget, I predict the cost to increase, since my slope is positive, by 73 cents, and I'll put 73 cents in parentheses. Okay, so $0.73 or 73 cents. All right, let's do the y-intercept. So this is basically saying a burger with 0 ounces will cost me 25 cents. Okay, I predict a burger with 0 ounces of meat to cost 25 cents. Okay, yeah, that really doesn't make sense. I'm not going to buy a burger without any meat. Okay, so I'm going to write does not make sense. And I always put a little frowny face. Okay, because again, not going to buy a burger that doesn't have any meat. Okay. All right, let's find and interpret the residual for a burger with a 3-ounce patty on the residual plot. So here's a graph of all of my residuals. Okay, let me try to zoom in a little bit. There we go. So for every ounce of meat, so there's 0, 2, 4, 6, 8, 10, 12 ounces of meat. These are my residuals. So 1, 2, 3, 4, 5, 6, 7. These are the 1, 2, 3, 4, 5, 6, 7 prices that are above the prediction. These are the residuals for the prices that are below the prediction. So if I go to 3 ounces of meat, which is going to be around here, this is my residual. Okay, so the residual, I'm going to guess, is about 0.75. Okay, so what's that, 75 cents? Okay, so my 3-ounce patty has a residual of about 75 cents. Okay, 75 cents. So let's interpret that. The 3-ounce burger's actual price is 75 cents more than I would have predicted. Okay, because again, let's go down here to 3 ounces. Okay, so here's 3 ounces. Here's my one that I am looking at. Okay, it costs a little more than what I would have predicted. Here's my prediction for 3 ounces. Okay, I'm gonna use a little red pen. Here's my 3 ounces. This is my prediction. This is the actual. So the residual is 75-cent difference. Okay. Now my question is, what is the actual cost? Okay, well, I could come up to this dot and go across, and I don't know, 350, 360 is my guess, but let's do it mathematically. If the residual is the actual minus the predicted, okay, I know the residual is 0.75. I can find my predicted by plugging in my equation. So if I did 0.25367 plus 0.734765 times 3, I would get a predicted cost of $2.46. So I don't know my actual, but I do know my predicted. So all I have to do is solve for y by adding these two together. Okay, so the actual price, sorry, I'm running out of room. My actual price is just the 246 plus the 75 cents, which would be the 321. Okay, so my actual price for my burger was 321. Okay, so I was pretty close. What did I say, 350? Can't draw my line straight. So my actual price is a little over $3, but I would predict a little over $2. Okay, so that's why my residual was 75 cents, which again, it's all up here on the residual plot. Okay, so these go together. All right, let's do a little bit more. All right, so let's predict the cost of a 1-pound burger or a 16-ounce burger. So again, I would just stick it into my equation. We do y hat equals, oops. And this time I'll put in 16 ounces. So if I stick that in the calculator, it gets to be $12.01. Okay, is this prediction reasonable? All right, so 16 ounces. If I look at my data only covered from about 1 ounce to about 11 ounces. So 16 ounces is outside the scope of my data. So this is not a reasonable, okay? 16 ounces is outside scope of my data. And my data goes anywhere from, 1 ounce to about 11 ounces. Okay, so this is called extrapolation. And again, we don't want to do that. We don't want to predict beyond what our data is allowing us to predict in. Okay. All right, now let's say a new restaurant opens in town and sells a 10-ounce burger for $12. If you add this burger to your data, what will be the effect on the correlation, the slope, and the standard deviation of the residuals? Okay, let's go up and add it. I'm going to put it in red. So a 10-ounce burger for $12 would probably be around here, okay? So that's going to have a 10-ounce burger I would predict to be maybe about $7 or maybe $7.50 or closer to $8. So $12 is really high. So I'm going to have a residual, pretty high residual, okay? I have a pretty high residual. So as far as my correlation, that point, that added point is going to pull my least squared regression line up a little bit, okay? So actually, let me talk about slope. So my slope is going to change. My slope is going to increase, okay? My slope is going to change. Now correlation, how tight are all these dots now to a linear form? This one's kind of far out. So my correlation is actually going to go down a little bit. Okay, it's going to get weak. It's going to get weaker. I don't want to say go down. It's going to get weaker. So what is my correlation? If my r squared, my coefficient of determination is 0.852, if I square root 0.852, that should be my r. Oh, my pen's running out of ink. So So if I square root that, I get 0.923. So before I added that extra burger in there, that expensive burger, my correlation was pretty tight, okay? Very strong positive linear association. And again, how do I know that's positive? Because my slope is positive, okay? When you square root, it's never going to give you positive or negative. You got to think about that, okay? So this is a very strong positive linear association. Well, if I put that extra burger in there, that 10-ounce burger for $12, that's going to get weaker. It's going to get closer to 0. So maybe it'll go down to 0.7 or something like that, but it is going to get weaker, okay? And then the last thing it talked about was the standard deviation of the residuals. Now, my standard deviation of my residuals is this S value. And again, if we remember from the other video, your standard deviation of your residuals is basically your prediction error. So when I use ounces of meat to predict cost, I'm typically going to be off by about 82, 83 cents, okay, when I predict the cost of my burgers. So adding that value that's going to have a high residual is going to increase that standard deviation of my residuals, which is going to mean my predictions are going to be off by more typically, okay? So putting them in there is going to wreak havoc with my, my prediction, okay? Okay, so here's a quick little analysis of our situation here. Now, taking the 10-ounce burger for $12 out, okay, not even thinking about him, would this linear regression have been a good model so that I can predict the price of the burger from the ounces of the hamburger patty, okay? Well, what we want to look at for that are three things. The most important thing is the residual plot. Okay, move this up a little bit. Our residual plot. This is the key to determining whether a least squared regression line is a good fit for data and the least squared regression line is a good way to predict your response off of your explanatory. So what we want from a residual plot is we want no pattern. Okay, this is what we want. We don't want it to look like a line. We don't want it to look like a curve or like parabolic or what is this, exponential, okay? So this is very scattered. This is kind of all over the place. So that's a good thing, okay? So we don't want a pattern. We want random residuals, okay? Typically you see about half the residuals are positive and the other half of the residuals are negative. So we've got some negative residuals, we've got some positive residuals. And again, I don't see a curve here. I mean, circle's not a curve. But I mean, if it was just like that, I would say, But then you got these guys up here. So this is good. This residual plot is good. There's no pattern. So is the least squared regression model a good model to, good fit to model the price of a hamburger based on the amount of meat? Yes. And I would say because the residual plot has no pattern. Okay, so that is the best way to determine whether a least squared regression line is a good model. Okay, let me zoom out a little bit. Okay, other things we can talk about, but I would always talk about the residual plot first. This is your number one thing. Are the coefficient of determination. Okay, so that's our R squared. So again, our R squared was 0.852. So if we interpret this, we would say about 85.2% of the variation in cost is explained by the least squared regression line relating cost to ounces of meat, okay? Okay, and again, we want that to be as close to 100% as it can, okay? So we want it close to 100%, okay? 85.2% is not bad, all right? So that's even more proof that this is a good equation to use to predict costs from how big the hamburger patty is, okay? Let's see, the last thing is, and of course, correlation kind of goes with coefficient of determination, but remember, correlation is just the numeric value of how linear the observations look. R squared is the numeric way to quantify how close the observations are to the least squared regression line. So this one's a little more important on using to prove that a least squared regression line is good. Correlation, not so much, because you can have correlation but not have a least squared regression line. Anyway. Okay, the last thing I want to talk about is standard deviation of the residuals. Okay, now our standard deviation of residuals, which is our S, is 0.829. So again, let me write down the interpretation. So when I use this least squared regression line to predict hamburger price from the size of the patty, I'm typically going to be off by about 83 cents. Okay. Of the patty. I'll say 8.3, which again is 83 cents. Okay. Now, what you want for our standard deviation of residuals, so that we know our least squared regression line is a good model, is we want it small. Okay, and I put small in quotes because that's going to be a relative term. 83 cents might be small here, but it might be large in a different context. So this one is a little harder to determine, okay? I mean, I guess 83 cents seems small in the grand scheme of things for a burger. I don't know, okay? So this one's a little harder to determine, okay? So what we want to do, again, in order to determine if a least squared regression line is good to use for predictions, residual plot is the first thing we want to look at. We want to make sure that residual plot has no pattern, no curve, no line, anything like that, okay? So ours looks good. The next thing we want to look at is our coefficient of determination and make sure that's as close to 100% as it's going to get, okay? So these are the two good ways to determine, okay? And again, standard deviation of the residuals, we want it to be small, but that's a relative term, so that's a little harder to justify sometimes, okay? Now, if it was like 0.00001 cent, yeah, that's really small. But 83 cents, I don't know. I guess that's small. Who knows, okay? But these two look good. So I think we can definitively say that this least squared regression line is a good way to predict the cost of a burger when we use the ounces of meat in a patty, okay? Because of all of our lovely information here, okay? I think that's it. So if we feel that we have a good linear regression line, then we can just go and do our predictions and feel good that our predictions will be as accurate as they can be. But of course, no prediction is ever 100% accurate, and that's okay. Okay, hopefully this was helpful, and I will see you next time. Bye-bye.